Good morning. We're continuing our discussion on preliminaries for college physics. We're having a brief look at vectors. We're having a look at vectors just enough so that we'll be able to master the material in this course. It'll be worth your while to look at vectors in greater detail later on. I recommend Show Outline series on vector analysis, or the Introduction to Vectors in Mary L. Bose's book, Mathematical Methods in the Physical Sciences, or any book on vectors, or even on the web. We're looking at elementary vectors. The last time we had vectors as the idea of devices for keeping track of components. We kept track of pieces of fruit in a bag, apples, pears, and lemons. That was looking at the components. When we added vectors, we added the components. We found also the length of a vector. The length of a vector is called the magnitude of a vector. We use Pythagoras' theorem to do that. A generalized Pythagoras' theorem to 3 dimensions works also, in fact, to any number of dimensions. So we had a vector example. In 2 dimensions. We don't really need the 3. Sometimes we'll use 3 just for the generalization of it. So this vector we will regard today as a little arrow. The last day I steered away from arrows. So we will say it's a little arrow today with length and direction. Now the magnitude of this vector is going to be 4. I'm going to change this to 4. This vector originates on the origin and ends up at the point 3, 4 if it was a Cartesian space in y and x. Okay, so 3i squared, 3 squared plus 4 squared, square rooted, gives me a magnitude of 5 for this vector. The magnitude of this vector is 5 units, wherever they might be, it doesn't matter. And let's see, what else can I say? Oh yes, and to construct a unit vector in that direction, we just divide this vector by its magnitude. That's the unit vector. The unit vector, we have a little hat on the top. The vector notation for us is a squiggle underneath. In textbooks, the vector is usually denoted by a bold-faced type. Okay, now let's consider another vector. Here's another vector. If we add them, we add the components. V1 plus V2 we will call R, the resultant of adding the 2 vectors. It's a 2-dimensional case only. So, where is this vector? 11i plus 6j. It ends on the point 11,6 and we'll put it in. So, here's our resultant, and we noticed something. We can add these vectors using the parallelogram method, because this is a parallelogram. Or we can make a triangle to add the vectors. this is the case for only two vectors. However, if you were to set it all up with a bunch of vectors, you would find that you can still add vectors by going tip to tail. So the triangle method is going to be the tip to tail method. So if we didn't actually have the components and we didn't have actually got the angles, we can still draw these things out. Let's have a look at the tip to tail method for lots of vectors. We begin at the origin, add them tip to tail, and end up at our resultant, which will be some vector that joins this whole figure and completes it, right? Any number of vectors, this works, and you can show that by simply plotting out the components on graph paper. I don't have time to go into this, it's only a YouTube lecture, but this can be done. Now we're going to look at a very special case that crops up all the time in problems. This case crops up in Newton's law of gravity or in Coulomb's law in electricity, things that you will come across. When we have a vector that's denoting the position of an object, it is basically an arrow that begins at the origin. We'll call this R1. Now R is the notation usually used for position vectors. So we have some object 1. Object 1 could be a mass, could be a charge, at position x1, y1, here. And we have object 2 at x2, y2. It is very often desired to have a vector between these two guys. We'll call this vector R12. How do we find R12? Well, R12 is a vector that joins the points x1, y1 and x2, y2. Well, here's what we notice. We we notice that if we were to take R1 and actually add it to R12, we would get a resultant which would be equal to R2. So R1 plus R12 will give me R2. Try and follow this because it crops up all the time. So R1 plus R12 is R2. So therefore then, if we subtract R12 from both sides, it's going to cancel here, and it's going to be left over here. Actually, I didn't mean to do it that way. We're going to subtract again. Let me do it slightly different. I'm going to subtract R1 from both sides. Gives the same thing, except that R1 is in that position. So therefore, this is our result. Very important result. It's simple, but people sometimes overlook it. To find R12 is the vector from here to here, is given by R2 minus R1. And a unit vector in that direction on that direction is the same old thing. R12 with a hat on it. And to put a hat on any vector, all you do is divide by its magnitude. You put a hat on it, you make it a unit vector. So R12 hat has magnitude 1. Let's clear the board and do an example. Now this is not going to work out exactly because I'm going to have strange numbers. I'm just going to drag them out of my head. I may as well put a mouse in. It's coming. You don't know about it yet. So we have two masses, one at 2,8 and one at 6,3. So the position vector in this case here is going to be a vector looking kind of like this. The position vector along here is going to kind of look like this. Okay? So R1 is going to be 2i plus 8j, and R2 is 6i plus 3j. Here's the question. Find a unit vector in the direction R1 to R2. So we're going to find R12 basically, and here's our formula. So R12 is R2 minus R1 over its magnitude. So we put in the numbers for that. R2 is 6 plus 3. R1 is 2 plus 8. Subtract them and we get that. Well, to find the magnitude, this is the magnitude, we just square the components. 6 minus 2 is 4i. 3 minus 8 is negative 5 times negative. Now we do every step. You don't let your head carry things like this. Big thing in mathematics and physics. Let your hands do the calculating. Then you get through it without making mistakes. 6 minus 2 is 4, which has to be squared. 3 minus 8 is negative 5, which has to be squared. Now in this step I will remove the bracket, giving me a positive sign. 4 squared is 16. 5 fives is 25. And I get 4i plus 5j over 41 square rooted. Now you know you can do that in your calculator, but you know, I'll do it just for the record. So that this particular vector has components 0.62 in the I direction and 0.78 in the AJ direction, and that is the unit vector R12. And where is it? It's here, going along that direction, but of unit length. Now we finish up with just a little bit of notation. This is a very common calculation. You will use it lots of times. I'm leaving a lot of practical applications of vectors aside until we actually arrive at problems. Problems such as resolving forces, problems such as projectiles. So they're getting left. They will crop up, not in this unit, in this whole unit, yes, but not in the vectors introduction. A lot of vectors is just learning notation, so I'm going to give you a little bit more notation. More general notation, which is going to be useful definitely if you do more advanced work, and certainly if you go to advanced physics or mathematics. So we're going to talk about the Einstein summation convention, the Kronecker delta, and later, when we do cross products, a more general Kronecker delta, it's called the Levi-Civita symbol. So the Einstein summation convention. Now you might have wondered why we were using notation involving sums of these components. Well, it really relates to the way the Einstein summation convention works, although people don't kind of notice that nowadays. Now the components of this vector are Vx. We'll call that V1. And I, we'll just call that E1, unit vector E1. Vy is V2, Y2, the second direction. J is a unit vector E2. And similarly for Z and K. In other words, the K vector is just E3. Now we're adding up these things, so we can use the summation symbol. Because we're going that plus that plus that. We're summing from I equals 1 to 3. Okay? Now Einstein noticed that when you have indices repeated, you can make this sign redundant, get rid of it. All it means is this: whenever you see a repeated index, sum over it. It's a powerful tool. And we could have a matrix represented in this notation. There could be lots of other elements in it. The same thing applies. I have two J's. There's only one I. But to get this result, I would sum over it. The component with V1, V2, and V3, and the matrix element MI1, MI2, and MI3. And I'm going to make this a kind of a matrix that only has diagonal elements. In other words, there doesn't exist an M12, there doesn't exist an M21, just M11, M22, and M33. And that's the way this summation convention works. You don't have to really master it now, just to know that it exists, because when the chance comes, I'll use it again. We have to do in our next lesson vector products. So coming next, I use the word in vectors because there are three. There's a scalar, multiplying by a scalar. next way to multiply a vector is to multiply vector 1 by vector 2 to make a scalar. And we call this the dot product. And the dot product is commutative. Commutative just means this. 3 4s is 4 3s. V1, V2 is V2, V1. Now what's the third way to multiply a vector? Well, you can guess, right? Here we just multiply by a scalar to make a vector. Let's say we multiply by 10, the new vector is going to be 10 units long. This one here we get a scalar multiplying two separate vectors. So now we get two vectors and in this case here we take vector v1, multiply it by v2 to make a new vector. Some new vector x, we will say. We can show that it's not commutative, it's anti-commutative. Anti-commutative means that instead of getting the vector, it's getting a number, getting v1 times v2 is negative v2 times v1. That means anti-commutative. You get a negative sign there. And what did they look like? v1 times v2 crossed in with each other is called the cross product. The new vector x is a vector that works like this. I take this back. I'm screwing in a light bulb. You screw a light bulb in that way to get a vector going that way. An anti-cross product is going this way. So your vector, you think about this. v1, oh I see, it was the other way. So v1 cross v2, v1 cross v2 gives me this new vector x. Now we'll play through these things the next day. That's enough for one class. We'll leave that for today. We'll have some examples as usual.